Welcome back to the deep dive. If you're involved in the rail industry, maybe as an engineering student, just starting your career, or, maybe you're just fascinated by how we move millions of people safely every single day, you understand the stakes. They're incredibly high.
Uh-huh. There's really no room for error.
Exactly. Zero margin.
Yeah.
Because when things go wrong on a railway, it's not just an inconvenience. The outcomes can be, well, catastrophic.
That's absolutely the fundamental truth. It drives everything in rail safety. I mean, the industry does have one of the best safety records globally, but that's not by chance, right?
Not at all.
It's maintained by just relentless rigor. We have to constantly prove and reprove safety. It's not a one-and-done thing when the tracks are laid.
And that proof, that whole story, the definitive safety narrative for any railway system, it gets captured in this, well, frankly, monumental document, often running into multiple volumes. It's called the safety case. And that's what we're diving deep into today. It's not just some checklist, ticking boxes for compliance. It's not just a stack of paper. It's really the foundation of trust. Trust between the engineers, the operator, the public.
Yeah.
And if you're an engineer coming into this field, getting your head around how this document is constructed, it's completely non-negotiable.
That really is the critical point. The main goal, the whole purpose of the safety case, is this comprehensive documented demonstration. First, that the system meets every single specified safety requirement. And second, crucially, that all the risks, all the potential dangers are mitigated so far as is reasonably practicable.
SFARP. We're going to hear that acronym a lot today.
We certainly will. SFARP. It comes from common law, but now it's basically embedded in rail safety laws globally. It's the ultimate measure, the thing that drives every single design choice, every operational decision.
So our mission for this deep dive is to kind of lay out the blueprint, the architecture of this vital document. We're going to really focus in on its core component, the Safety Assurance Report, the SAR.
The heart of the matter.
Exactly. And look at how the industry leaders use specific tools and standards to wrestle with the, frankly, immense complexity involved. And when it's done well, the results speak for themselves. You look at systems like, say, the Dubai Metro.
Yeah, a great example.
Right. Effective safety cases directly translate into top-tier operational performance. They achieve incredible figures like, 99.7% trained availability and punctuality.
That's right. And that kind of operational resilience, that's the real-world payoff. It shows this rigorous approach really works.
Okay, so let's try and structure this, a big topic. When we say safety case, what are we actually talking about? It's the definitive central record, right?
Yeah.
Of everything safety-related throughout the entire life of a system.
Entire life, that's key. From the very first concept sketches, through design, building it, operating it, maintaining it, all the way to eventually taking it out of service, decommissioning it, maybe decades down the line.
Wow. So to manage that massive scope, the safety case is basically built on 3 pillars, 3 core interconnected parts.
That's the standard way to think about it, yes. 3 pillars. And they absolutely have to work together. Auditors, regulators, they look at all 3 elements to decide if the overall claim, this system is safe, actually holds water.
So if one pillar is shaky,
the whole argument collapses. Doesn't matter how safe the system might look on the surface. If the documentation isn't sound across all 3, it fails the assessment.
Okay, pillar number 1, we've mentioned it.
Right.
The Safety Assurance Report, the SAR. You called it the heart, the core engine. Why is this central argument document so vital? Can't we just, point to the hazard log? Is that where the risks are?
That's a really good question. The hazard log is, well, it's essential, but it's essentially raw data. It's a huge list, right? Identified risks, how bad they could be, what controls are in place, but the SAR provides the story.
The narrative.
Exactly. It's the rigorous, joined-up justification for why, after looking at all those hazards and controls, the system is acceptably safe to run. Why the risks really are SFARP. Think of it less like a technical spec sheet and more like, I don't know, a lawyer's closing argument.
Okay.
Meticulously structured, backed by solid evidence, it communicates a clear, comprehensive, and importantly, defensible reason for safety. And crucially, for auditors and regulators, the SAR is the ultimate roadmap.
A roadmap. How so?
It shows complete traceability. It lets them follow the thread, say, from a high-level safety goal, like prevent collisions between trains, all the way down to the specific bit of code or the specific test result that proves that goal has been met. Without the SAR, it's just a pile of information. The SAR gives it structure and meaning.
Got it. So the SAR is the argument, the brain. Pillar 2 then would be the supporting documentation. This sounds like where the real engineering heavy lifting happens.
Precisely. This is the vast amount of input generated by all the critical safety analysis processes. This is where engineers apply their deep technical expertise. It includes all those standard methodologies that, frankly, every engineer entering the field needs to get comfortable with.
Like?
Well, starting right at the beginning with preliminary hazard identification, the PHI. That then feeds the preliminary hazard log, the PHL, which is a living document throughout the project, but it goes much, much deeper. We pull in detailed risk analysis reports like the system hazard analysis or SHA, and then the really granular systematic stuff.
Can you give us an example? What are these systematic techniques?
Sure. A classic one is fault tree analysis, FTA. That's a top-down approach. You start with a major undesirable event, say, a train derailment, and you work backwards logically. You map out every single possible combination of failures, human errors, external events, component failures that could potentially lead to that top event. It's deductive.
Okay, working back from the worst case.
Exactly. And then there's the other side of the coin. Failure modes and effects analysis, FMEA. This is bottom-up, inductive. Here, you take every single component, maybe a brake actuator, a specific chip on a circuit board, and you ask, right, how can this thing fail?
Like stuck open, stuck closed.
Exactly. Short circuit, leaks, gives the wrong signal, slow response. You list all the conceivable failure modes. Then you ask, what's the immediate effect of that specific failure on the subsystem and then on the overall system? It's incredibly detailed work.
Wow.
And these documents, the FTA, the FMEA, the hazard logs, they're born from just intense, rigorous technical examination. They are the building blocks that prove you've really thought through all the ways things could potentially go wrong.
Okay, that makes sense. So argument, the analysis, supporting docs. Pillar 3 must be the evidence base. This sounds like the hard proof.
It is. This is the concrete, you might say indisputable proof that you didn't just talk about safety in endless meetings. You actually built it, you tested it, you verified it.
Show me the data.
Pretty much. This is where you find the final sign-offs on test results. The stamped and approved design drawings, the installation check records, the verification reports that prove the system actually does what the specification said it should do. It closes the loop.
So if the SAR is the argument and the supporting docs are the research,
then the evidence base is the cold, hard proof. Without that meticulously collected and referenced evidence, the whole safety case is considered, well, flawed. Because the claims made in the SAR haven't been properly substantiated, they haven't been explicitly justified with real-world proof.
Right. Okay, let's dive deeper into the SAR itself then, the Safety Assurance Report. You called it the roadmap. If it's the central navigation tool, what absolutely has to be inside it for it to be considered complete and defensible to an auditor?
Good question. The SAR needs a very clear, often quite rigid structure to manage all this information effectively. Right at the top, right at the apex, you have the safety argument itself.
The main conclusion.
Exactly. But it's not usually pages and pages of dense text. It's often a clear, concise, high-level summary. And critically, it needs to be formally signed off by the relevant authorities, the people accountable. It basically asserts the final conclusion. All the necessary controls are demonstrably in place, and the risks have been proven to be reduced SFARP. It's the headline statement.
Okay, the conclusion right up front. What comes before that, foundationally?
Well, underpinning that summary, you absolutely need the safety requirements and objectives. These lay out the big picture goals, the overall strategies, the fundamental rules that define what safe operation actually means for this particular system, whether it's a brand new signaling system or a fleet of refurbished trains. This is where you set the measurable targets for safety performance.
Makes sense. And then you mentioned this earlier, the crucial contextual information. You really emphasize this for auditors. Why is context so important in a safety case? Isn't safety just safety?
But safety is never in a vacuum. It's always specific to the situation. So this section defines the technical world, the operational environment the system lives in. It includes the detailed specifications of those safety requirements. What must the system do to be safe? And, absolutely critical, it must reference all the applicable standards, codes, and criteria that dictate how you have to achieve that safety.
And when we talk standards in rail, you almost immediately think of the CNLX standards, right? They seem to be the bedrock, especially in Europe and many other parts of the world.
They really are the foundation for functional safety in rail. Anyone working in this space simply has to know them. There are three core ones we always come back to.
Okay.
First is EN 50126. This standard defines the overall process for managing RAM's reliability, availability, maintainability, and safety across the entire system lifecycle. It basically tells you how to run the whole safety management show from cradle to grave.
Got it. The how-to guide for the process.
Precisely. Then you get more specific. EN 50129 is vital. It focuses specifically on safety-related electronic systems for signaling and control. Think hardware components, interlockings. It lays down the strict processes and documentation you need to prove that the hardware itself is safe.
And the software, that's covered too.
Absolutely. That's EN 50128. It deals specifically with the software within those safety critical control and protection systems, how you develop it, how you test it, how you validate it. Together, these standards, especially 50129 and 50128, really enforce a rigorous development approach, often visualized as the V model.
The V model, right, where testing happens against requirements at each stage.
Exactly. Verification and validation are built in throughout the design process, not just tacked on at the end. So in that contextual information section of the SAR, you're basically stating, here's the goal, here are the physical limits, and here's the rule book, the standards like Synelec that we followed.
Okay, so goal, boundaries, rules. What else is in context?
It also has to detail any significant project or development constraints that shaped the scope from the outset. Maybe budget limitations, maybe interfaces with legacy systems, and crucially, it must explicitly reference back to all those supporting documents we talked about Pillar 2, the hazard logs, the FTAs, the FMEAs. That chain of traceability has to be crystal clear. An auditor needs to be able to pick a requirement from EN 50129, follow the reference in the SAR, and land directly on the specific test report or analysis that proves compliance. Without that seamless link, the argument just falls apart. Now, this leads us into what is arguably one of the trickiest and most critical parts of the contextual information. That's managing assumptions, constraints, and dependencies, or ACDs.
ACDs, right.
This is an area where, honestly, a lot of safety cases can become flawed if these aren't handled very explicitly, documented properly, and formally agreed upon.
I think for people listening, especially if they're newer to this, the difference between these three assumptions, constraints, dependencies can be a bit fuzzy. Why are they so vital in this context section?
Because they essentially define the edges of the system's responsibility. They clarify what the safety case covers and what it relies on from the outside world. If you're depending on something external to your system's design or operation to maintain safety, you absolutely have to state it upfront. Let's break down assumptions first.
Okay, please do.
An assumption is basically a statement that the team doing the safety assessment can't prove, or maybe doesn't need to prove right now, but they believe it to be true. And crucially, they expect it to stay true for the entire life of the system without needing ongoing active management or monitoring as part of the system's safety case. It's taken as a given for the risk analysis to even begin.
So what's the big risk? What happens if an assumption turns out to be wrong later on?
The risk is huge. If an assumption fails years down the line, the whole risk assessment that was built upon it could become invalid. The safety logic just crumbles. A classic example might be related to the track itself. The safety argument for a new train control system might rely on an assumption like track maintenance will be performed by the infrastructure owner according to specification XYZ at the required intervals.
Okay.
Now, if, unbeknownst to the train control supplier, the track owner cuts corners on maintenance, maybe extends the intervals, or uses substandard materials, the conditions the train control system was designed and proven safe for no longer exist. That's why the assumption must be crystal clear, so the rail transport operator, understands exactly what foundational conditions their system's safety relies upon.
That distinction is really important, something taken as fact versus something that needs active managing. Okay, let's move to constraints. How are they fundamentally different?
Constraints are different. They're limiting conditions that are accepted on how the system can be operated. They define the absolute boundary conditions for the safety argument to be valid. Think of them usually as physical or operational limits that the operator must stick to throughout the system's life.
So if you operate outside that boundary, the safety argument might be immediately invalidated. Poof.
Precisely. Imagine a section of curved track. The safety assessment might determine it's safe for trains up to, say, 120 kilometers per hour, based on the track geometry, the cant, friction calculations, everything. So a constraint would be stated clearly in the SAR. Maximum operational train speed on section ABC shall not exceed 120 kilometers.
Okay.
If an operator then runs trains at 130 kilometers on that section, they've gone outside the defined safe operating envelope. The risk assessment that justified the safety case for that speed no longer applies. And here's a key point. Constraints are not the right place for conditions that need active management or monitoring, or depend on continuous human action. Those things are operational requirements. They should be listed in the hazard log as controls that need managing. Constraints are fixed boundaries. Controls are active measures.
Got it. Fixed boundary versus active mitigation. Okay, and last one, dependencies. What's unique about them, especially when it comes to signing off the system?
Dependencies are essentially actions or activities that aren't finished yet, but they must be completed, usually before the system goes into passenger service. Often, these involve interfaces with other systems or work being done by other contractors.
It sounds a bit like a project snagging list.
It can feel like that, but the safety implication is critical. The final risk assessment, and therefore the final safety case sign-off, cannot be considered truly complete until every single dependency has been closed out, verified, and any resulting impact assessed.
Wait. Can't you just assume they'll be done correctly?
You can plan for it, but you can't certify safety based on an assumption about future work being done right. Because the way that dependency is actually closed out might introduce new hazards or change the risk profile in ways you didn't foresee.
Oh, okay.
Consider a dependency like, safe operation of our new signaling system depends on the civil engineering contractor providing sufficient electromagnetic shielding in the line-side cable decks. Now, if the final installation is checked and that shielding is found to be poorly installed or damaged,
The risk of interference goes way up.
exactly. Suddenly, the risk of signal interference, which could be incredibly dangerous, is much higher than assessed. You might need immediate changes to the hazard log, maybe even costly rework. So you absolutely cannot issue that final safety certificate until every dependency is confirmed complete, the outcome assessed for any new or changed risks, and everything formally verified.
And tying this all together, there's a crucial administrative step, right? All these ACDs, assumptions, constraints, dependencies, they don't just get listed. They need formal acceptance.
Absolutely essential. They must be clearly laid out in the SAR and then formally accepted, signed off by the organization that will ultimately operate the railway, the Rail Transport Operator, or RTO. This act formally transfers the ownership and responsibility for managing these contextual factors from the supplier or project team to the operator before the system carries passengers. It's a critical handover point.
Okay, this really highlights the complexity. Which brings us neatly to the next major challenge, managing all this complexity. A railway isn't just one thing, is it? It's this incredibly intricate system of systems built by experts from totally different fields.
It really is. You're trying to get engineers who live and breathe software code to effectively communicate and integrate their safety arguments with engineers who deal with, tons of steel, high voltage power, complex mechanical linkages, hydraulics, pneumatics.
And it's not just the traditional engineering fields either, right?
Not at all. Increasingly, you have vital inputs from disciplines like human factors. How does a driver, maybe tired at the end of a shift, interact with a new display screen? What are the psychological factors in decision-making under pressure? All these diverse perspectives have to be woven into that single coherent safety argument presented in the SAR.
So you've got all these technical silos, maybe using slightly different jargon, different ways of thinking about failure, and they all have to feed into one document. That sounds potentially chaotic, a recipe for ambiguity.
It absolutely can be. Just gathering those different views on how components interact, identifying potential system-level safety issues that fall between the cracks of different disciplines. That is consistently one of the hardest parts of developing any safety-critical system. And if you try to do that synthesis using just, say, massive traditional text documents, 500-page Word files, incredibly complex spreadsheets, tracking hazards, you inevitably hit problems. Consistency issues, traceability gaps, difficulty checking for completeness, and just sheer lack of clarity. It becomes almost impossible for anyone, even the safety experts, to hold the entire argument in their head.
So how does the industry tackle this? How do the leaders manage this huge integration and communication headache?
The big shift, and it's becoming increasingly mandatory in many contracts, is the use of goal structuring notation, or GSN.
GSM.
Yes, it's a graphical method. It's visual. It's specifically designed for documenting and communicating the safety argument, primarily within the SAR. What it does, essentially, is take the argument out of those dense paragraphs of text and turns it into an explicit, structured diagram. It makes the logic transparent.
A visual language for safety arguments. What are the real advantages of that? Why is a picture, in this case, worth maybe 1,000 pages of technical text?
Well, ambiguity is safety's worst enemy, right? GSN helps eliminate a lot of that. Because it's graphical, it forces an explicit structure onto the argument. This dramatically improves clarity and understanding, not just for safety specialists, but for all the stakeholders involved.
Even non-safety people.
Yes,
Yeah.
potentially. The product manager, the system engineers from different disciplines, the client, the regulator, they can all look at a GSN diagram and grasp the basic structure of the argument much more easily than wading through hundreds of pages of text. It also makes it far easier for assessors to check the logical flow and, critically, the completeness of the argument.
Completeness, how so?
You can literally trace the links on the diagram. You can see a top-level safety claim, follow how it's broken down into subgames, and see exactly what evidence supports each piece. If there's a claim node hanging there with no supporting evidence linked below it, that gap is immediately visible. It's much harder to hide gaps in logic or evidence in GSN compared to dense prose.
That sounds incredibly valuable. Can you quickly break down the main building blocks of GSN? What are the core elements we'd see in one of these diagrams?
Sure. There are basically four main types of elements, all linked together. At the top, you typically have goals. These are usually shown as parallelograms. Goals represent the claims you're trying to prove about the system's safety. The big statements like, the braking system reliably stops the train within the required distance.
Okay, that's a big claim. How do you prove that?
That's where strategies come in. These are often drawn as rectangles with rounded corners. A strategy describes the approach, the method you're using to break down that big goal into smaller, more manageable sub-goals. So the strategy to prove the braking goal might be something like, demonstrate safety through rigorous analysis, A&D comprehensive testing.
Okay, breaking it down. And the actual proof.
That comes at the bottom, in the solutions or evidence nodes. These are often shown as circles. They are the terminal nodes. They represent the actual concrete evidence that satisfies the sub-goals stemming from the strategies. This is where you point to specific documents. Test report number 123, FMEA analysis, document XYZ, the relevant section of the design specification. This is the hard proof.
Right. Goals, strategies, solutions, evidence. Was there a fourth?
Yes, context, often shown as a simple rectangle. Context nodes provide necessary background information or clarify the scope for a particular part of the argument. This is where you'd reference the specific standards being applied or define key terms, or importantly, link to those assumptions, constraints, and dependencies we discussed earlier.
Ah, so the ACDs get explicitly linked in.
Exactly. GSN basically turns that potentially overwhelming mountain of text and data into a clear, traceable, visual map of the entire safety justification. It's a powerful tool for managing complexity. And it's vital to remember all this work, GSN diagrams, hazard logs, it's not just theoretical paperwork. It underpins the safety of real-world operational systems carrying millions of people. Their success hinges on the accuracy and completeness of this safety case.
Let's talk about some of those real-world applications. You mentioned the Dubai Metro earlier. The Roads and Transport Authority there, the RTA, they're often highlighted as a leader in safety implementation.
They really are. The RTA's approach is a fantastic example of how adhering to safety case principles drives tangible operational results. The Dubai Metro has an independent safety assessor continuously monitoring their compliance with international standards, specifically following that systematic lifecycle process laid out in EN 50126.
And that rigor pays off.
Absolutely. It translates directly into those headline figures we mentioned. 99.7% availability and punctuality. That doesn't happen by accident. It's achieved through really robust safety management systems and preventative maintenance programs that are designed based on the risks identified and controls defined way back in the initial safety case development.
And it's not just about train performance, is it? Their safety focus seems much broader.
It is. The RTA rolled out a huge 5-year health, safety, and environment plan, the HSE plan, with something like 133 specific initiatives. And you can see the results in public safety statistics, too. They've managed to dramatically reduce system-wide fatality rates, across all their transport activities from historical peaks down to fewer than 4 per 100,000 people. That's a massive improvement.
And they're not standing still. They're looking at new tech.
Right. They're actively bringing in things like AI and other fourth industrial revolution technologies to help monitor HSE standards continuously. It shows that the fundamental principles of the safety case have to be dynamic, they have to adapt and integrate with these new technological capabilities.
We see a similar story perhaps with the Doha Metro in Qatar, another very advanced system built to high standards.
Yes, the Doha Metro project really underscores the value of getting that independent assurance involved early. They appointed an independent safety assessor, Ricardo in this case, right back in 2012 from the very beginning.
Why so early?
To ensure passenger and staff safety was embedded throughout all the design and development stages, not just checked at the end, they developed comprehensive operational safety cases, FOSCs, to meet really demanding certification targets. And they achieved them. For instance, their critical fire safety systems were certified to Safety Integrity Level 2, SAL2.
SL2, that's a significant level of assurance for something like fire safety.
It is. It reflects the potential severity if those systems failed. And crucially, like Dubai, they have very strict processes for managing change. They use something called a Request for Operational Change, or RFOC. This means that any proposed change, doesn't matter how small it seems, a software patch, a minor tweak to trackside equipment has to be formally assessed against the original safety case arguments before it gets implemented. Nothing changes without a safety check.
That idea of constantly assessing change really hits on a core principle you mentioned, the safety case as a living document. It can't just be finished, signed off, and then put on a shelf to gather dust.
Absolutely not. Change is inevitable, isn't it? User needs evolve, better design solutions emerge, maybe regulations change. Our understanding or acceptance of certain risks might shift over time. Because of that constant flux, the Safety Assurance Report, the SAR, and indeed the whole safety case must be treated as a living, breathing document.
And the challenge is maintaining it.
The huge operational challenge is ensuring its consistency, its completeness, its correctness, day in, day out, in the face of all that change. If an organization treats the safety case as just a bureaucratic hurdle to overcome to get permission to operate, a one-time deliverable, they've fundamentally misunderstood its purpose and, frankly, compromised long-term safety.
Managing such a massive, evolving document must have been a nightmare historically. I'm picturing rows and rows of binders, version control chaos with Word documents, maybe complex spreadsheets trying to link everything.
Oh, it was, and often still is in some places. Those traditional paper-based or simple file-based methods make audit trails incredibly cumbersome. It's hard to trace relationships between requirements, hazards, controls, and evidence. And there's a really high risk of inconsistencies creeping in between, say, the latest design documents and the safety case that's supposed to reflect them.
But digital tools are changing that.
Thankfully, yes. Digital transformation is making a huge difference here. We're seeing the rise of dedicated, computer-based safety case management tools. These aren't just file repositories. They provide structured data management, often using databases. They can automate version control, manage links and traceability, and give much better visibility and collaboration across different engineering teams.
Can you give an example of this in action? I think Network Rail in the UK had a significant project, RailHub.
Yes, RailHub is a brilliant case study. It was designed to replace these incredibly cumbersome 60-page, paper-based safe work packs that track maintenance crews had to carry and fill out.
60 pages.
Yeah. By digitizing the whole process, safety planning, risk assessment for the specific job, briefing the team, getting electronic sign-offs, they achieved truly phenomenal results, and results that directly impact lives.
Like what?
They reported a 95% reduction in the use of their riskiest standard working method, which involves staff being physically on open lines with lookout protection. 95% reduction. And alongside that, a 50% reduction in reported near misses between track workers and trains across their work sites.
Wow, those are incredible numbers.
They really are, and it shows the power of making safety information accessible, usable, and integrated into real-time operational decisions. It validates that living document idea digital tools allow the safety case principles to be actively managed and demonstrably improve safety outcomes on the ground.
Okay, let's shift gears slightly and look at the bedrock, the standards and legal principles. We keep mentioning CENELEC. They really are the regulatory foundation for all this system safety work in rail, aren't they?
They are the technical cornerstone, globally recognized. Just to quickly recap the main ones again, EN 50126 sets the overall RAMS process. EN 50129 covers the safety-related electronic systems, the hardware, and signaling logic. And EN 50128 deals with the software running inside those systems. Together, they provide the framework for achieving and demonstrating high levels of functional safety. And that leads directly to the concept of safety integrity levels, or SLs.
SLs, right. This comes up all the time in safety critical systems. You hear SL1, SARO2, and SL4 For our audience, what does that decile rating actually mean, especially SL4, the highest level? What level of safety are we talking about there?
SI4 represents the absolute highest level of safety integrity defined by the standards. It's reserved for functions where a failure would almost certainly be catastrophic, leading directly to multiple fatalities or severe environmental damage. Think of functions like the core automatic train protection, the ATP system, that prevents trains from passing red signals or overspeeding.
So what does a system have to achieve to get SL4 certified?
The standard, primarily EN 50129 for the system level, mandates an incredibly low probability of dangerous failure. Specifically, the rate of dangerous failures must be less than 10 deliveries per hour of operation.
10 to the minus 9 per hour. That sounds tiny. Can you put that into perspective? What does that mean in real-world terms?
It's difficult to grasp, but 10 deliveries per hour translates roughly to expecting less than one dangerous failure in about 10,000 years of continuous operation for a single system function.
10,000 years.
That's the kind of reliability and assurance target we set for those absolutely critical, must-not-fail functions in railway control and protection systems. Obviously, systems performing less critical functions, maybe auxiliary systems or certain communication links, might only require SIL1, SIL2, or SIL3, but the underlying principle is the same. The higher the SIL, the more rigorous the analysis, the more stringent the design techniques, the more evidence is required, the more independent assessment is needed. The effort scales exponentially with the SIL level.
And all these standards, the cell ratings, the detailed analysis like FMEA, they're all driving towards satisfying that fundamental legal principle you started with, SFARP.
Exactly. So FAR is reasonably practicable. It's worth repeating because it's so central. It's not just a technical target. It's the modern legal test for whether an organization has exercised sufficient duty of care.
Derived from common law, you said.
Yes, centuries of it, now codified in most modern health and safety legislation worldwide. It acknowledges that you can't achieve zero risk. That would mean stopping the railway altogether. But it places a legal duty on the operator to reduce risks to the maximum extent that is reasonably achievable, considering the cost, time, and effort involved in taking further measures versus the safety benefit gained.
Okay, so how does an engineering team, or the operator, actually prove SFAAP in the safety assurance report?
Yeah.
How do you defend the level of risk that remains?
It's usually a combination of approaches, documented in the SAR. Firstly, you rely heavily on good practice arguments. You demonstrate that you're applying established, recognized, well-documented engineering practices and standards that are widely accepted and used successfully in similar railway applications around the world. Following the Sinelec standards is a major part of this.
So basically showing you're doing what's considered best practice by the industry.
Yes. Secondly, you use expert judgment. This involves relying on the formal, documented opinions and assessments of competent, experienced engineers and safety professionals. Their assurance activities and conclusions form part of the argument. And thirdly, particularly for situations involving novel technology, very complex interactions, or where the residual risk is still significant, you often need quantitative analysis. This usually means performing a formal cost-benefit analysis, or CBA.
Ah, the CBA. This is where safety engineering meets economics, right? Balancing cost against risk reduction.
Precisely. A CBA is a structured way to demonstrate that the cost of implementing an additional safety measure would be grossly disproportionate to the safety benefit it would actually deliver.
Grossly disproportionate. That sounds subjective. Is there a benchmark?
It can seem subjective, but regulatory bodies often provide guidance or apply common tests. For example, Transport for London has historically used ratios like 3-to-1, meaning if the cost of the extra safety measure is more than 3 times the calculated monetary value of the risk reduction it achieves, based on preventing fatalities, injuries, damage, etc., then implementing that measure might be deemed grossly disproportionate.
So you might be able to argue SFAP has been met without that specific expensive measure.
Yes, provided you've already implemented all other reasonably practicable measures, the CBA helps justify where you draw the line. It's the systematic process of identifying risks, applying controls, following good practice, and then potentially using CBA for the really tough residual risks that allows you to build a defensible SSAP argument.
Okay, given all this complexity, the technical depth, the legal nuances of SARP, the need for traceability, it really underscores the need for an objective viewpoint, doesn't it? Which brings us to the role of the independent safety assessor, the ISA.
The ISA role is absolutely critical, often mandatory for getting a system certified for operational use. They provide that independent, objective judgment. Crucially, they must be completely separate organizationally and financially from the teams designing, developing, or operating the system they're assessing. No conflicts of interest.
And what exactly does the ISA do?
Their responsibilities are pretty broad. They review basically everything related to safety: the hazard logs, the analyses, the test plans and results, the SAR itself. They verify that the project is actually following the required standards, like Senelec. They assess the effectiveness of the whole risk management process. And ultimately, they provide a formal, unbiased safety opinion back to the project and the regulator about whether the system is ready and safe enough for its intended use.
Is the main benefit just having that external stamp of approval? Or is it more than that?
Oh, it's much more than just a rubber stamp. That independence builds confidence for the operator, for the regulator, for the public. It helps eliminate internal biases or pressures that might lead teams to cut corners or accept risks that they shouldn't. The ISA provides a holistic view looking not just at the documents, but also at the processes being followed, the competence of the teams, the underlying safety culture.
And getting them involved early helps.
Massively. As we saw with the Doha Metro example, bringing the ISA in early during the design phases is invaluable. They can spot fundamental safety issues or non-compliances when they're much easier and cheaper to fix, preventing significant rework, cost overruns, and project delays later on.
Okay, so pulling this together, especially for those listening who are newer to rail safety, when things do go wrong, when incidents happen and investigations occur, what are the common themes? What are the typical pitfalls or organizational mistakes that investigations reveal, even when complex safety cases exist?
It's sobering, but incident investigations often highlight recurring failures. 3 areas come up again and again. First, and perhaps most fundamentally, incomplete hazard identification.
Just not spotting the danger in the first place.
Exactly. Investigations often find, and sometimes state quite bluntly, a serious failure to identify risks to safety. This can happen for many reasons, maybe organizational blind spots, poor communication between different engineering teams, a failure to properly consider how humans will interact with the system, especially under stress or fatigue. If you don't even identify a hazard, you obviously can't control it, and the safety case is built on shaky ground from the start.
Okay, failure to see the risk. What's the second common theme?
The second is inadequate management of external interfaces. We touched on this with dependencies. Systems don't exist in isolation. If you look at investigation reports, a significant number, maybe 10% or more in some analyses of UK incidents, for example, point to failures related to how the system interacted with external parties.
Like maintenance crews, other contractors.
Yes, or utility companies working nearby, even adjacent infrastructure operators. The safety case has to clearly define the boundaries, the responsibilities, and the controls needed for every single interface with the outside world. Assumptions aren't enough. Interfaces need active management.
And the third major theme, it often comes down to people and processes, doesn't it?
Absolutely. The third is organizational failures. Ultimately, safety isn't just about technology. It's deeply rooted in organizational culture, procedures, and competence. We've seen historical crashes like Bexley in the UK years ago, where investigations found that fundamentally unsound working practices had been allowed to persist over long periods. Maybe safety data wasn't being properly collected or acted upon, training was inadequate, or there was pressure to prioritize schedule over safety.
Complacency creeps in.
Complacency, normalization of deviance. These are symptoms of deeper organizational issues. And perhaps the biggest organizational failure is treating the safety case itself as that tick box exercise, that one-off deliverable we talked about, instead of embedding it as a living, breathing part of how the railway is managed every single day. That mindset often underpins many of the other failures.
So for our audience then, the engineering students, the early career folks wanting to make a real contribution in rail safety, what skills should they be focusing on developing to be effective in creating and assuring these complex safety cases?
Well, mastering the standards is a given. But beyond that, I'd highlight 3 key areas. First, systems thinking. The ability to see the big picture, to understand how all those different disciplines, software, mechanical, electrical, human factors, interact and contribute to overall system safety, not just focusing on your own silos.
Seeing the connections.
Exactly. Second, you absolutely must master the fundamental hazard analysis techniques. Get really comfortable with PHA, HAZUP, FMEA, FTA. These are the core tools of the trade. And third, and this is increasingly critical, develop strong, structured documentation skills. The ability to communicate complex arguments clearly and logically is paramount, and proficiency in methods like GSN is becoming a huge advantage, almost essential in many places, because it provides that clarity and defensibility across different teams and stakeholders.
So systems thinking, hazard analysis mastery, and structured, maybe visual documentation skills.
Precisely. Roles in system safety engineering are in very high demand across the industry globally. Mastering this knowledge, understanding the principles of the safety case, that's really your ticket to entry and making a meaningful impact.
What a journey. We've gone from the high-level legal principles like SFARP and the extreme reliability demanded by SIL 4, right down through the nuts and bolts of hazard analysis, the structure of the SAR, and even the graphical language of GSN. It really drives home that the safety case isn't just one thing, it's the integration point for everything. Technical design, legal compliance, operational procedures, safety culture.
That's the perfect summary. It connects everything. And if we look at the bigger picture of where safety management is heading, the industry is trying to shift. Moving away from what's sometimes called safety arc-up, which is mostly about learning reactively after things go wrong, learning from failures,
Right.
towards safety too, which is about proactively learning from everyday success, understanding why things go right most of the time, understanding how systems and people adapt and create safety in dynamic situations, and mastering the development and maintenance of a robust living safety case is absolutely fundamental to enabling that shift towards a more proactive, resilient safety culture.
That leaves us with a really interesting final thought for you, our listeners, to mull over. We're seeing the rapid emergence of autonomous trains, AI being used for real-time monitoring and even decision-making on railways. The complexity is just going to keep increasing. So the challenge for the next generation of engineers won't just be documenting safety for systems designed by humans. It will increasingly involve using these explicit, structured, perhaps visual methods like GSN to argue for and assure the safety of systems that are constantly learning, adapting, maybe even writing parts of their own operational code based on machine learning. How do you structure your safety story? How do you build that foundation of trust when the system itself becomes an active participant in its own evolution? Something to think about as you embark on or continue your journey in rail engineering.
Thanks for listening to Safe Tracks, the Systems Safety Assurance podcast. Here, we talk all about how safety assurance keeps our railways running safely, smoothly, and reliably every single day. If you're curious about RAM management, RAM analysis, and how reliability is actually calculated, check out the RAMs Ready podcast playlist on this channel. It's packed with great insights. And hey, don't forget to subscribe and tap the notification bell so you'll know the moment a new episode is out. Until next time, stay safe, stay assured.